to understand why it doesn't feel that we're moving. You have to go all the way to Einstein, really, for someone to take that very seriously. And he said, actually, he said, well, this, there's a great little explanation in Stephen Hawking's Brief History of Time about this, that the idea that you can't see where you're moving
Kill confirmed.
demolishes the notion of absolute space. So if we think about space, if I said space to you or most people, I suppose, we think of the way that Newton did it, the big box in which things happen. And that's got to be that's a natural picture of space. The thing you move. In the history of time, Hawking says, well, imagine bouncing a ball. So we bounce a ball on the table now, a tennis ball. I drop it and I catch it again. So let's say I drop it, it takes a second to bounce up. So in that second, the Earth has moved about 18 miles.
KIA confirmed.
So you could ask the question, did that ball return to the same place in space or not? And the answer is, you can it does from altitude.
Tossing sticky
But we
grenade!
expected a similar thing, the whole way around. So it went up by caught it again, it had moved 18 miles. And then from some other perspective, it would have done something else. So the point is, this is a point in space. It's coming back to the same place. Because that depends on your perspective. It depends on whether you're watching the sun, the Earth go around the sun or whatever.
Friendly UAV on
So
station.
Einstein said that means there's no such thing as absolute space. Which is, kind of follows if you think about it. But that's a difficult, it's a cool but difficult thing to process.
Right. I mean, that's essentially what's happening when you're on a plane. I mean, if you're throwing a ball up in the air and catching it on the plane, it's happening at a much smaller scale, right?
Yeah. I mean, you're flying at whatever 600 miles an hour relative to the ground.
But it doesn't
there's
seem
no-
like it when you're sitting there.
Yeah, and Einstein elevated that to a principle and said, if you're moving at if you're not accelerating, you're just moving at a constant speed in a plane, or now. I mean, that's essentially what we're doing now. We're moving around the sun at effectively constant speed. Then you can't tell. So there's no experiment you can do. We could look at the decay of a radioactive nucleus, magnetism, or bounce a ball,
Confirmed
a
one.
pendulum, whatever. And there's no experiment you can do to tell you whether you're moving or not. Therefore, that concept has no meaning. Because you can't measure it. And that's led Einstein to relativity.
Wow.
So that's the basis of general relativity, which is the best theory of the universe.
But why is it that we think larger than what we can observe?
Well, one point is that it's
Hostile UAV in the area.
expanding, and we always see the same radiation out there, so the glow of the Big Bang. But there are some deeper reasons.
Dropping ammo here!
That one, from the
Semtex!
theory of inflation, the best way to explain the universe, the properties that we see, is that it's very much bigger.
Friendly cruise
than
missile
things
approaching
we see.
target.
So, for example, we measure space.
Changing map!
Tag
I don't
secure.
say what's
Kill
all flat,
confirmed.
is flat. So if you imagine slices of space, let's imagine slices of them at different
Confirmed.
times.
Enemy
So you just
KIA.
slice the universe and say there's a big sheet, it's like this table.
Okay, like a
There's a
table.
sheet of space, there's another sheet, and it can have a geometry, right? It can be flat like
Oh,
a
shit!
tabletop,
Amateur shit!
like a sphere, or it could be curved in the opposite direction, sort of like a saddle or a bowl. And we can measure that. And when we measure it, we see it's absolutely flat. And that's a very unusual thing for it to be like. It requires, because what Einstein said, that the shape of space, that the curvature of space is determined by the stuff that's in it. It's based on Einstein's theory of general relativity. Puts stuff into space, curves it and bends it and warps it and stretches it and so on. And what we find is that we have precisely the right amount of stuff in the universe to have a completely
The enemy
flat
has the lead.
universe. And the explanation, the most favoured explanation of that is the universe is way bigger than the piece we can see. And so it's like looking at a piece of the Earth. If you look at a little 1 mile square of the Earth, it's flat. You have to look at big distances, kind of avoid the radius of the Earth.
High alert online.
Bigger than 1
Confirm the kill.
1 mile.
Hostile counter UAV overhead.
And that's one of the ideas about the universe and why it
Enemy
appears to be the
UAV
way that
active.
it is, because it's way bigger. So we're just looking at a little piece, and that's why it looks flat. And that's one of the ideas.
Now, when you say
Tossing
flat,
sticky grenade!
like that,
Kill confirmed.
is from our perspective, when you look up at the Milky Way, you see all these stars, all of these. So if you're saying flat, like what? How much? What are you saying?
So the best way to think about it is not to think of 3 dimensions of space.
Mission is half complete.
Well, you can
Secure
think
the
of 2,
victory.
like this tabletop, and that's all right. We can set it down. And so you know what this table. I mean, you could define it. So you could say, for example, that if I draw a triangle on the top of the table, then all the angles
Ammo
are
here!
280 degrees. So that actually defines flat. If you did that on the surface of the Earth with a big triangle, then the angles wouldn't add up to 180 degrees. Or you could draw a circle
Confirmed.
and say
Enemy
what
KIA.
Holy shit! I'm sorry, Steve First Soldier.
that's only true. Flat.
Friendly counter UAV is online.
So you can define flat.
But you're saying flat is what is the height and what is the width? Like if you're talking about
Our UAV is
there
orbiting
must be
the
some sort
area.
of there's a dimension to it, correct?
Oh yeah, there's a 3rd dimension of space,
Right.
but the same applies. It's just a generalisation of geometry. So you can pick. The point is, but you can draw. You can quite literally. You can imagine sending light beams out. And we do this measurement actually. We can look at the most distant background radiation, which is if you imagine looking out. If you look at the Andromeda Galaxy, which we can see naked here in LA, you can see that it's the most distant. It's about 2 million light years away or so, which means the light takes 2 million years to get to us. So it's a long way away, but it's very big. So as you look further out into the universe, to more and more distant galaxies, you're looking further back in time. You look at something that's 1 billion light years away, then the light is 1 billion years to get to us. So we see it as it was.
Friendly UAV online.
And we can
Confirm
actually
the
look
kill.
so far out that we can see almost back to 13.8 billion years ago, which is
Friendly
very
counter
close to the
UAV
Big
is on
Bang.
station.
So we can look to light on its journey before the Big Bang. And that's the oldest light in the universe, which is, by the way, one of the pieces of evidence when people say I don't believe in the Big Bang. The answer is, well, you can see it. So you know, it's just there. You can see it. We have pictures of it. That light, it turns out that there are sort of structures or ripples in there, which there's a ruler in the sky. And then because that light's been travelling through the universe, we can see how that ruler's been distorted as the light has travelled through space. And so we can infer whether space is flat or curved or how it's warped, if you like, just from that measurement. It's a beautiful measurement.
Is it possible that in the future we'll be able to see 13.8 billion years?
Not with light.
Not with
because
light.
what the picture is that before it's actually was released 380,000 years after the Big Bang. You might say, how do you know that? Well, before that time, the universe was so hot that atoms couldn't form. So you had a soup of electrically charged particles. It was just too hot for electrons to go into orbit around nuclei. So the universe was opaque to light. So you just couldn't. It's like almost like a big glowing star.
Got that one.
And then when it was expanding, it cooled.
Don't let
At
up.
that point, it
KIA
expanded
confirmed.
really almost instantly in a cosmic timescale. And so the light could then travel in straight lines through the universe. And we can see that
What's your
light.
name?
So we see the light from that further. It's opaque, so you can't see past that with light. But you can, potentially, with gravitational waves, which is this measurement that got the Nobel Prize years ago. And that looks for ripples in the fabric of space and time.
Our
And in
counter UAV
principle,
is active.
if we had a
Last
big enough
minute.
detector, you could see the ripples from the Big Bang. So you could use an image of the Big Bang in gravitational waves.
Time
But
secure.
you need an
Kill
enormous
confirmed.
space-based detector. So,
No, obviously this is all through equipment and technology that's been invented over the last few hundred
Friendly
years and
UAV on
perfected.
station.
Is it possible that things could get better and you could get some ability to detect things even far more distant?
yeah, I mean, gravitational waves are incredible. I mean, Einstein predicted that nothing could be. Never thought they'd be detected. because you need such a high. You need lasers. They didn't have
Right.
lasers. But the thing, LIGO,
hunters,
this experiment,
mission
which is half
accomplished.
in up
Lack a
near
job.
Seattle in Washington State, and half in Louisiana. So they've got 2 detectors, and they're basically sort of 3-mile long laser beams that just sit and measure the sort of stretching and squashing of space as the ripples in the fabric of the universe go through. And what they've been observing are collisions of black holes. So you can imagine how extreme, like a colliding black holes. It's an incredibly extreme event. So it shakes the fabric of the universe, and the ripples come across the universe. And these laser beams, which are just basically rulers, can detect it. They just sort of ring almost like, just vibrate as the ripples go through.